In the previous video, we simulated a model on the target and observed the difference between running as quickly as possible and running in real-time synchronized mode. In this video, we will learn how to monitor our simulation's execution performance. But first, let's review what it means to run a model in real time. What constraints do we face running in real time? Starting with our PID model as an example, let's assume three things. 1. It is using a fixed step solver. 2. The time step defined by the user is 1 millisecond. 3. The time to solve the distance equations at each iteration is 0.5 milliseconds. Now, the question is, how much time does it take to complete 5 time steps? 5 time steps represents 5 milliseconds in the simulation. When our model is configured to run in simulation mode, it executes as quickly as possible with no CPU idle time. Therefore, it would take 5 times 0.5 milliseconds, or 2.5 milliseconds of real-world time. In other words, the simulation time would run faster than the time of a clock on the wall. In software synchronized mode, after calculating for 0.5 millisecond, the target simply waits for the rest of the 1 millisecond time step to elapse before proceeding to the next iteration. This idle time is, in a sense, a waste of computational power because the target is doing nothing during that time. However, this ensures that the simulation time progresses exactly at the same rate as actual wall clock time. The 5 time steps will therefore take exactly 5 milliseconds in both the simulated environment and in real life. Real-life simulation is mandatory, for instance, for hardware-in-the-loop testing or for rapid control prototyping. However, what if, for some reason, the computation block took more time than the defined time step in the solver? For instance, what if it took 1.2 milliseconds instead of 0.5 millisecond to do the computation? Is it still respecting real time? The situation we've just described is called an overrun, and in this context, the next step is abandoned and only the subsequent step is executed. In other words, it means that the simulation environment was delayed by 1 time step as compared to real world. Ideally, there should never be overruns for real-time applications. Practically, it may be acceptable to have some overruns at the beginning of the simulation for the initializations, but this is the designer's decision. However, it is mandatory that the number of overruns does not increase or accumulate as time elapses, because this indicates the simulation is running slower than real world and means that slowed down signals would be fed to the external device. This is not representative of real-world conditions and thus is not acceptable for real-time applications. The presence of overruns indicates that we should either increase the simulation time step or consider using more computation subsystems to respect the real-time constraints. Back to the example model. How can we confirm that the model does not have overruns and how much execution time is required? This will ensure that the model respects real-time constraints and let us know if we can expand the model using the current configuration. Performance monitoring can be done in 2 ways. First, by using the Monitoring tab in RTLab. Second, by adding the Op Monitor block to the model. To observe the performance through the Monitoring tab, we need to set the Enable Monitoring parameter in the Diagnostics tab. Once the model is loaded and executing on the target, we can navigate to the Monitoring tab. We have the option to get probes once or get probes constantly. If the probe is not indicated in green, this means that none of the subsystems in the Project Explorer was selected. We can see the simulation time, CPU utilization, overruns, and the real simulation time step, which factors in communication delays. In this example, the SM subsystem has low CPU usage and no overrun time steps. The other way to monitor the execution performance is by adding op monitor blocks to the model. This block is found under Monitoring in the RT-Lab library. We can send the output of op monitor block to the console subsystem, where we will add displays to allow us to dynamically observe the performance values in our Simulink console during execution. Note that each subsystem can have an op monitor block. After recompiling the model, loading and executing the model, the results are displayed in the console. The main advantage of the op monitor block is that we can use it to add custom logic to the model. For instance, to disconnect an output if we have an overrun. The output of op monitor can also be recorded for post-processing analysis, as presented in a subsequent video.